Hi everyone, we're starting our next lesson, lesson 17, continuing with expansion, different types of expansion. Today we're going to be looking at section 3E and 3F on difference of squares and perfect squares. Okay, so let's start with difference of squares. Now what we're going to do is I'm going to just very quickly write out for you what the solutions are to these problems. And we're going to try to come to the conclusion on what's going on. So for example, if I've got two binomials here, they seem to be practically identical, the binomials. Take a look at all of the examples we have here. We've got x minus 2 times x plus 2. We've got x minus 4 times x plus 4, x minus 3 times x plus 3, x minus 8 times x plus 8, and so on. They all seem to be identical, the only difference being that within the binomial, the two terms are the same. So the x's are the same, the values of the two are the same, but one of them happens to be positive and the other one happens to be negative. And when we have this type of situation where we have two basically identical binomials, but one of them is positive and the other one is negative, what we end up having is what we call a difference of squares. And what that involves then is, now, multiplying the first terms and the last terms together, so that I would say x times x, I would multiply x times x, which would give me x squared, and then I would do 2 times 2, which gives me 4. And because it's negative 2 times positive 2, it's just minus 4. Same thing would occur over here. We would have x times x would be x squared, and negative 4 times positive 4 would give me negative 16. Now why does this happen? This basically happens because if we tried to FOIL it, which we could use FOIL here if we wanted to. Let's take example number 3. So we have the x minus 3 multiplied by x plus 3. If I tried to FOIL this, I would have x times x gives me x squared, x times positive 3 gives me a positive 3x, negative 3 times x gives me a negative 3x, and a negative 3 times a positive 3 gives me a negative 9. When I simplify the terms here in this expression, I end up getting that the positive 3x and the negative 3x cancel themselves out. And therefore, I'm left simply with x squared minus 9. So what's actually happening is that when we've got a difference of squares, in other words, definition, difference of squares, you have two basically identical binomials. The terms inside the parentheses are the same. The only difference being that one of them has a positive in it, the other one has a negative in it. When I have this situation, instead of actually having to FOIL the whole thing, where then my middle terms, the middle x terms get cancelled out, all we do is we take a shortcut and we say, well, we just square the first term and then square the last term. So we square the first term, and then we square the last. And then what would go in the middle, though, is obviously going to have to be, what we have to put in the middle, though, is always going to have to be a negative, because a negative times a positive, and like in all of these cases, negative 8 times positive 8, negative y times positive y, negative 3 times positive 3, and so forth. They will always go to a negative. Now let's take a look at some of the other examples. So we said, because we've got two identical binomials, but one is negative and the other one is positive, then I just square the first term, which is x squared. I square the last term, which is 9, and I put a negative in the middle, or a minus sign. If I do number 4, I have x minus 8 times x plus 8. Again, I recognize this as being a difference of squares. Identical binomials, the signs change. One is a positive, the other one is a negative. So that I will square the first term, x goes to x squared, and I square the last term, 8 squared is 64, and I put a negative in the middle, or a minus. Same thing occurs even when my terms become more complicated. 2x minus 3 times 2x plus 3. Okay, so again, we've got identical binomials. The terms inside the parentheses are identical. We have 1 minus, we have 1 plus, therefore it's a difference of squares, and therefore I square the first term. 2x squared means it's 2x times 2x, which is 4x squared, and I square the last, which is 3 times 3, which is 9, and we put a negative in the middle. And then we've got the last one, x minus y times x plus y. I square the first, x squared. I square the last, y squared. And I place a negative in the middle. Okay, that would be the difference of squares. And again, the rule is simply square the first, square the last, and put a negative in the middle. And when do we use this rule? We use it when we have two identical binomials, so the terms inside are identical, A, and B, and B. Okay, they are identical, but one of them happens to be positive, and the other one has to be negative. Okay? So in that case, we would square the first, square the last, and put a minus in between. And again, just to remind you, if I have A plus B times A minus B, I could use FOIL. I could FOIL this, but the foiling process will show me that I get A squared plus AB minus AB, or minus BA, means the same thing, minus B squared. And the middle AB term cancels itself out, and all I'm left with is just A squared minus B squared. So that would be the difference of squares. Let's take a look at some other examples. So very quickly, I'm going to ask you to do these examples for me, and then you will put them in the PlayPosit. And you'll place these in PlayPosit. Okay, next section, perfect squares. Perfect squares means exactly what it is. It basically means that you have identical binomials in every sense. So, for example, I've got x plus 2 and x plus 2, x minus 4 and x minus 4. Those are my two identical binomials. I don't have one as positive and the other one as being negative, but I have them as being identical. Okay? Now, again, I could FOIL these, and let's FOIL it. Let's try it out by FOILing. So x times x gives me x squared. X times 2 gives me 2x. 2 times x also gives me 2x, and 2 times 2 gives me 4. I now add my like terms together so that I end up with x squared plus 4x plus 4. Now, I used FOIL on this, okay? But there is a shortcut method. Again, what we do is, I've shown you with the difference of squares, I'm showing you with the difference of squares and perfect squares, I am showing you some shortcut methods to use for expanding or getting rid of our parentheses without having to FOIL every time. Sometimes it's faster to do it this way. If you recognize the perfect squares, when you recognize the difference of squares, you don't need to use FOIL. Alright, so let's use the example of A plus B times A plus B to see what our pattern is here. Because I already know what my pattern is, but we're going to go through it. So when I use FOIL here, I end up getting A squared plus AB plus another AB plus B squared. And I end up with A squared plus 2AB plus B squared. Okay, so what is the rule basically telling me? The A squared plus 2AB plus B squared is basically saying that I am going to be taking my first term and I'll be squaring it. So I am squaring the first term. Okay. And then I'm essentially squaring the last term as well, because I'm doing B squared. So square the last term. And then the middle term, though, doesn't disappear, unlike in the difference of squares, where I have one being positive and the other one being negative. Here they're either both positives or they're both negatives. Okay? And so, what is the middle term telling me that I have to do? The middle term is telling me to take the two terms that are inside the binomial, A and B, and multiply them together. A times B, there it is. A times B. I do A times B, and then I multiply it by 2. So I find the product. So find the product of the terms in the binomial and multiply them and multiply it by 2. And multiply the product by 2. That is what you would do every time. Okay, so let's use an example here. X plus 1 times x plus 1. I know it's a perfect square. There are two identical binomials. So using the rule that we have up here, it says square the first term. So squaring the first term is x squared. And I square the last term. Squaring my last term here is plus 1. It's 1 times 1 is 1. Okay? Now, I take my first and second term inside that parentheses. So x times 1 is just x. And then it gets doubled, or it gets multiplied by 2. So I take the product. I take the product of what's inside the binomial, inside the parentheses. I multiply those two terms together. X times 1 gives me x, and then I multiply them by 2. So it becomes 2x. Let's try the next one. So it's identical binomials. I square the first, x squared. I square the last, positive 16. Negative 4 times negative 4 will give me positive 16. I now say x times negative 4 gives me negative 4x, and then I multiply it by 2. So it goes to negative 8x plus 16. Next one. We have square the first, 4x squared, square the last, 9. Now is a positive 9. I now do 2x times 3 is 6x. I multiply that by 2, and that gives me 12x. So I'm done. Now, again, let me repeat. You can FOIL. You are allowed to FOIL here, but it is easier when you've got perfect squares and difference of squares. It is easier for you to use these shortcut methods. So just to recap, let's just do a couple of examples. So if I've got, let's take for example number 8 here. I've got a minus 2b all squared. Again, I can FOIL it, but because they're identical, a minus 2b times a minus 2b, then I will say a squared, square the first, square the last. 2b times negative 2b is 4b squared. Then I multiply a times negative 2b. That gives me negative 2ab, and that gets multiplied by 2. So it's negative 4ab. Okay, let's do 6 minus a. Let's do number 4. 6 minus a all squared. So that I will square the first. I will square the last, a squared. Then it's 6 times negative a is negative 6a times 2 is negative 12a, and it's plus a squared. All right, I'm going to leave the questions that I circle in blue. I'm going to leave for you to work out on Play Pause It and put your solutions in. So I'll ask you to do 2, 5, and 11. All right, that's basically it. Your work is here. It's exercise 3E, numbers 1 through to 3, all of it, and 2 through to 6, all of it.